Our next talk is on a subject that whose idea was conceived here at Rice by Rick Smalley and was something he had great hope for, and the talk will be given by a colleague of mine, Howard Schmidt, and the title of the talk is Developing the Quantum Wire. Howard?
Good afternoon. Let me see. Okay. Wade, Amy, thank you very much for the opportunity to speak here. It's a great privilege. It's a little humbling, too, get to speak between Paul Chu and Alan Wendell and Ray Bachman. Been very privileged to work with Rick Smalley for the last couple of years and work on the Quantum Wire project, which has been a real trip. I also have the privilege of working with Wade Adams and Bob Hauge and a number of great scientists and grad students here. So I'm going to be talking today about our program to develop the armchair quantum wire. And this is largely a work in progress and a scientific saga. And let me see, how do I do this? That one? Where's my page down?
These buttons right here.
Okay. Thanks. So anyway, I'm with the Carbon Nanotechnology Laboratory. I serve as the executive director. The lab was founded by Rick Smalley as director. Bob is the technology director, and our principal commercialization partner is Carbon Nanotechnologies Incorporated, which is out on the west side of town. Oops, wrong way. And we don't do this all by ourselves, even though we have about 35 people in Rick's group. We have a great team of collaborators, both here and across the country. We have 10 folks 10 faculty people that we work with here at Rice, largely Jim Tour and Ed Billups for functionalization chemistries and Andy Barron for catalysis and inorganic and organometallic work, and Boris and Matteo and Bruce Weissman and the rest. It's a great team of people to work with. I think all told we have about 60 or 70 people working on various aspects of single-wall carbon nanotube research. We also have some collaborations at various other universities like University of Pennsylvania and Georgia Tech, as well as some NASA centers. Our funding comes from the folks down here. I need to acknowledge them too. So one of the first questions to answer is, why would you have a center just to talk about or to work on single-wall carbon nanotubes? My bottom line is that I think it's the ultimate engineering material. That's what I discovered when I first met Rick and started looking at this material. And my background's originally as an engineer. So in terms of, it's got all these just extreme best-of-class properties. And by the way, I will be giving a bit of an intro, since I'm leading off 3 talks on carbon nanotubes, on overview of carbon nanotubes, and then tell you what we're doing in terms of platform technology development and a little bit of applications for the wire at the end. So the carbon nanotubes themselves, you can think of as a polymer of pure carbon, and it's like a sheet of graphite rolled up into a cylinder, and it's extremely strong just due to the basic physics of the strength of the carbon-carbon bond. Strongest fiber possible, or strongest molecule possible, has extremely high conductivity, has a whole book of organic and organometallic chemistry, and has a scale and perfection. It's basically a large, it's a giant molecule. It has a scale and perfection of DNA. And uniquely amongst polymers, it has great electronic properties. Turns out that there are several different types of nanotubes. There's not just a nanotube. There's actually several hundred different varieties of them. There are conformations. And some of them have metallic properties, and the pure metals are actually better conductors of electricity than copper. The semiconductors are wide bandgap, not wide bandgap, but they're direct bandgap semiconductors, kind of like gallium arsenide or indium antimonide. And they have the highest carrier mobilities of any semiconductors known. So you put all that together, so you have one chemical system that has great strength, thermal conductivity, can be an insulator if you functionalize it, can be a great conductor or a great semiconductor. Great versatility in one system. That's why I think of it as the ultimate in engineering materials. Now, the project that Rick asked me to focus on is what's called the Quantum Wire Project. Now, this is a typical Rick project. It's the hardest thing you can think of in terms of nanotube research. He liked to work on the hard problems first. And one of the great benefits of that is as we make progress on this, we're developing platform technologies that can spin off and enable many other applications, whether it's in terms of composites for structural applications, or whether you're making soluble nanotubes you can turn into biosensors or biological therapeutic agents. There are lots of benefits along the way as we're developing the quantum wire. Now, sort of the bottom line of why this is an interesting project is we expect that a macroscopic assembly of armchair nanotubes would have conductivity greater than copper, perhaps as much as 10 times better than copper, at about 1/6 the density, stronger than steel, zero thermal expansion. And so this would boil down to, this would not be anything like a superconductor, but it would have better power advantages compared to normal conductors like copper or aluminum, probably on the order of 10 to 30 times better power densities. Now, if you applied that to a grid application, there'd be obviously less power loss, low to no sag, which is a great source of, tremendous source of failure modes in the grid, lower mass, so you have lower infrastructure or tower investment, and higher power density. You can get more power, you might be able to get more power through a given corridor or right-of-way. I've already discussed the issues of the spin-off benefits. Let me tell you a little bit about the electronic properties, and these are well known at the level of a single molecule. This is some work done by K.S. Decker and Rick Smalley some years ago. If you take a single nanotube and you put a voltage across it and measure the current, you can actually get on the order of 20 to 50 microamps of current through a single molecule. That, if you normalize that to the cross-section of the tube, that's on the order of 10 to the 9th, or a billion amps per square centimeter. That's unlike anything else known. Now, this is kind of a bit of a cheat because you got this one molecule sitting on a great heat sink. So I don't think you would never get that in a macroscopic object, and it's also fairly lossy. Here you're exciting some optical phonons here, losing about 1/10 of an eV per phonon scatter. But the nice thing about this, and this has been repeated in many labs, is you have a nice long mean-free path. It says that in this channel, in the channeled conduction, there are very few scattering events, just due to the symmetry and small diameter, reduced dimensionality of the system. You don't have side scattering modes. And here, just in this particular experiment, it's easy to get twice the conductivity of copper. There's some other, if we make a bulk conductor, you're not going to have one nanotube that goes from here to Dallas, for instance. You're going to have a collection of nanotubes, so we have to be concerned about conduction of electricity from one tube to another. We don't have samples of pure armchair nanotubes right now, so we have to resort to some modeling. This is some nice work done in the Carolinas a couple of years ago that would indicate that if you have pure armchair assemblies, that if the tubes overlap by more than about 1/10 of a micron, the transmission coefficient would approach 1. In other words, the resistivity would be quite low. And in fact, there's been some very nice research done by Tobias Hertel on Bucky tube mats, where basically you can measure the mean free path and lifetimes of excited carriers, and from that infer what the mean free path is, and thereby infer what the resistivity is. And this was done on Bucky papers made out of HIPCO, so it's a mixture that is not, again, all armchair metals, but this is the key thing. The numbers indicate a 10 to 25 times the conductivity of copper. So that gives us some physics basis for why this is an interesting project. Let me talk about the distinction of the various kinds of nanotubes. It turns out that single-wall nanotubes are stable up to about 3 nanometers in diameter, or about 30 angstroms. About 1/3 of them are what's called semi-metals, or metallic. 2/3 of them are semiconductors, and only about 2% of them are high carrier density true metals. And so if you turn, and it depends, those electronic properties depend upon how you roll up that piece of graphite. And so what we need to do is get NM control over the production. That forms the first of 2 major core projects we work on. We call it the SWIN Amplifier project. And so what we envision, if I get it right here, is taking a sample of pure nanotubes at a very small scale, cutting them into very small seeds, functionalizing them organically to generate individuals, adding a catalyst back to it, reducing that and docking it to the tube, and then growing it, putting it back into a growth reactor and growing the tube out. And so that's a pretty complicated process where we're trying to take what happens all automatically and rapidly in the HIPCO reactor and do it step by step with control at the individual molecule level. And we've been approaching this for several years and have several approaches. One of them is what we call a continued growth of fibers, where we take a macroscopic fiber, cleave it off, and then add catalyst to the top of that and put it in a growth reactor. This is a publication came out about a year ago, where I think this is the first demonstration of renucleating tubes in a macroscopic assembly and growing them out. And we're not making great baseball bats out of this stuff. We've grown about 10 microns of material. But the spectroscopy down here indicates we've created no new kinds of material, but have actually nucleated, added catalyst to the existing nanotubes and grown them out. That work has been progressing some. We've got better ways of cleaving the fibers off, like with focused ion beams, cleaning them off to expose the nanotubes, and growing a little bit more material. This project is ongoing, largely with support from the Department of Energy, and is making pretty good progress. Now, the bigger program that we call the SWIN Amplifier program is more of a solution-based approach, where we would take well-defined catalyst particles and then organometallically attach them to the nanotubes. This is one of our prototypes. We call this FEMOC. It's about 110 atoms of iron and molybdenum. It's very nice in that it's chemically precise, and it's got a very, very well-defined dimension of, say, 2 nanometers in diameter. We'll take that and cut nanotubes with well-defined chemistry at the ends. These will form dative bonds and form a complex, and we can deposit these down one at a time or in groups and put those on surfaces and study this chemistry one step at a time. Here's an example of some of the attachment chemistry. We're actually adding one particle at a time to a given nanotube. This is an atomic force microscope, so we can track this at a very fine scale. And this is what's called a cryo-TEM, or a transmission electron micrograph, of a frozen solution of these catalyst particles in a liquid. Oops, we have a picture missing. Well, take my word for it. There's supposed to be a picture over here that's basically this substrate with nothing on it. It shows that basically in a hydrogen environment, you can take that catalyst, activate it, and it just turns the nanotubes into methane. There it is. Okay. Well, you tricked me up. Let me see here. Wow, there's lots of it. And so this is an example of one of our prototype development experiments. We've taken, you can see, one nanotube here at a time. We've added catalyst here. This turns out to be a different catalyst. It's an iron oxide catalyst. We've roughly tripled the length of that one nanotube. Now, it turns out this is not obviously a bulk growth technique, but this is to study the individual unit processes so we get a handle on what's going on. There is another technique for growing nanotubes. It's called Kite Growth. This was done in collaboration with Jay Liu at Duke University. This is an example of the kind of growth you can get what's called tip or kite growth. Essentially, people talk about the lifetime or the efficiency of catalysts. In this particular environment, if the catalyst is growing freely in space, you can grow centimeters. I think the record now is 4.2 centimeters. And they actually grow at phenomenal rates. So what we've been working on lately is taking this tip growth, what I call the Immortal Catalyst, because these have been grown out. In fact, frankly, nobody knows how long they can grow. They seem to stop only when you run out of substrates where you can measure them. And marry that to a system where we can get the catalysts off of the surface. And so we've been working with seeds that are very fine dendrites that are free of substrate interactions. The substrates like HOPG seem to slow down the operation of the catalyst. And so this has been work that's been developed just in the last couple of weeks, where from seeds like this, we're growing material that's actually pretty woolly. And quite remarkably, we're growing yarns now that are millimeters, and in fact now centimeters in diameter, in length. These are about 10 microns in diameter. Now, we don't think that we know that this is not all seeded growth, but I think that this is partially seeded growth. But very importantly, this is a nice way, this is a demonstration of a way to do macroscopic scale immortal tip growth, which I don't think has been demonstrated before. This is probably scalable. We're trying to figure out how to do that, and potentially continuous. And that kind of touches on the next couple of talks where you see fiber work done by Bachman and also Wendell. Very interestingly, we've actually measured the current. We can run current through these individual yarns, and it turns out through these things that are not of theoretical density, we can get easily 10 milliamps. And these are current densities on the 10 to the 4th to 10 to the 5th amps per square centimeter, which rivals the useful current density of a lot of superconductors. So we think this is very promising, and it's a good step towards making a quantum wire. This is sort of a scale-up path here. How am I doing on time, Wayne? Okay. Now, the other big job in making a quantum wire is to take the tangled material that comes out of any growth system and essentially recrystallize it into a well-ordered array for maximum current density. This is an example of what we want to end up with. This is actually not a quantum wire. This is a fortuitous TEM, comes out of a laser oven system we think is primarily 1010 armchair tubes. This is the kind of structure that we want to end up with. It's a cross-section of a rope. What we typically start out with is a bucky paper or bucky mat like that. If you zoom in, it's a loose tangle, and if you zoom in tightly, you can see that you don't get optimal packing because you've got to have a variety of diameters as well as a variety of electrical types. You have some semiconductors and some metals. What we want to end up with is all true metals in that kind of packing density. So it's a pretty significant recrystallization problem, which kind of glosses over a lot of liquid crystal and basic physical chemistry. That's wonderful science. But the key issue is that these tubes are sticky. They like to adhere to each other, and we can only really get them apart or lubricate them in superacids. It was discovered here a couple of years ago that in superacids these tubes will intercalate and swell and become lubricated, kind of like here. And they'll actually end up forming wonderful liquid crystal domains like this. We call these spaghetti, which can then be aligned using shear flows and extruded to form macroscopic fibers. If you take that fiber and put it back in superacid, you'll see it swell. So this is sort of a reversible intercalation process. So we've been working on the details of scaling this up. We can make 100 meters of fiber at a time. These are not wonderful conductors or mechanical things at this point because as they condense, they tend to form fibrils that are not well connected to each other. So our core activity here is the basic physical chemistry of extrusion and coalescence. And so we've been working on improving that morphology and what we call the connectivity of the system. We've been making pretty good and steady progress on this. So for instance, back in 2004, that was sort of the morphology of our best fibers, which within about 6 months transformed into this. This sample at higher resolution looks like that. And so we're actually getting rid of the structure and making steady progress on this. So we are hopeful that over the next, say, 2 years, we'll be able to combine advanced crystallization techniques with armchair pure metals and end up making small samples of armchair quantum wires. As I say, this is probably a couple of years from fruition on the demonstration level, which puts us 2 or 3 plus 20 years from any kind of a market application. It's not quite a done deal yet. We have plenty of challenges. There's lots of great science left to be done. Now, here I am talking in the middle of a bunch of really great grid experts, so I'm going to zip right through this because there's plenty of other great information about grid applications. But the bottom line is that if you model what a 3x or 10x conductivity conductor would act like compared to your standard ASCR type conductor, which is it's a large, like inch diameter aluminum cable, you could get 10 to 30 times the kind of power density through it. Now this is not lossless. It's limited by the temperature rise in the system, just like this one is. But it probably has a higher surface service temperature rating because these tubes are stable in air to several hundred degrees centigrade and they don't sag. So the failure modes are quite different than they are for an aluminum-based conductor system. And this is Roger's stuff, and I'll skip that. But the key thing is that regardless of whether we're talking about an armchair quantum wire or Paul Chu's or American superconductors, superconductive cables, we do need to have a new class of transmission technologies sometime in the next couple of decades. We need to have like a 10x type solution because, as you can see now, our power production is typically located on the order of 100 miles from where it's consumed. Over the next few decades, as we shift increasingly to renewable sources, those sources are a lot farther away, more like on the order of 1,000 miles instead of 100 miles. And that's true whether you're talking about geothermal technology or solar or biomass or wind. It's the Midwest, Southwest, and such. Typically pretty far away from your major population centers. So that's a long way to move electricity through lossy cables, and some new class of solution is needed. And for instance, this is Nate Lewis's slide about how much solar area would be needed to replace our current electricity consumption. And so like the superconductive application areas, the early winds would be in short haul, high density links, basically in congested urban corridors, and then eventually in long distance high power applications for the remote renewables. So we don't work exclusively on just that, but we're now getting into a bunch of other application areas, which kind of spans the gamut, some of which are biologically oriented, some of which are energy oriented. But all of this is really enabled by the core platform technologies of catalysis and functionalization and processing that have been developed to drive in the process of driving the armchair quantum wire. But now, having kind of compressed the grid part, I'd like to take a minute to kind of throw out an editorial. And this is something I haven't test-driven with Amy or Wade, so I don't know how this is going to go. I'd like to remind you of kind of the vision that brought a lot of us together, which is the energy problem so well articulated by Rick Smalley. He called this the terawatt challenge. There's a terawatt, okay. Okay. I'll close quickly. So anyway, I'd like to throw out sort of a straw man. Rick had a great vision, but I would like to throw out that we would be well served to generate what I would call some Smalley challenges in the areas of generation, transmission, and storage, and model them loosely on this great thing called the Ansari X Challenge, which took probably 25 years to achieve. It's only a $10 million prize, but it generated a lot of excitement through the Spaceship One and this flying thing, which resulted in demonstration of private space flight. And these are typically 10x goals. Maybe they should be higher goals based upon total cost of ownership. In terms of, I'd like to limit this to solar at such a level that would make fossil fuel obsolete for, say, power transmission, not for transportation fuels. 10x in terms of power transmission, and 10, maybe 30x for energy storage. If these three things put together, and it's kind of drive a stake in the ground and inspire a generation of technologists, I think we can make the storage and grid a reality. And we should aim high. Thank you. Can you speak up, please?
In case of Cvd, catalyst particle diameter determines the tube diameter. Mm-hmm. You saw a very interesting slide there, AFM, where you have individual tube around 5 nanometer diameter particle and 1.6 nanometer tube diameter.
Yeah.
So it's kind of different. Did you observe frequently that kind of image? It's very interesting because that's a key how to control the diameter. If this is not working, so what tool else to get?
That's a good observation from someone skilled in the art. It turns out that particular catalyst is not active for growing the nanotubes, but it's quite active for etching. And that one's also a little bit misleading because that was the oxidized form. It probably shrank by a factor of 2 once it was reduced in the docking process. But the catalyst that we find will actually grow the tubes out, or rather closely matched to the diameters of the tubes. Yeah.
Any other questions? Not? Thank you, Howard.
Thank you.
I think our next speaker may have traveled the farthest to be here from England. Alan Wendell, and his title is Spinning Carbon Nanotube Wire. Alan?
Fine. It's a great privilege to be here. Also, it's a great privilege to get to know Rick Smalley over the last few years, and obviously we're all here with a sense of loss. I'm going to talk to you about carbon nanotubes and how they're going to be useful, particularly, of course, focusing in the area of electrical transmission. But there'll be rather more to it than that. This is the group at Cambridge. As with most things, people change, they come and go, and this is a snapshot as of about 6 months ago. But this is the team. And in fact, they cover a wide area of carbon nanotube-based material science. We've got up here the making of fibers, which is an area we'll concentrate on. Over here, we've got projects active in the use of carbon nanotubes for energy storage. But particularly the axis of friendship developed with Rick Smalley was focusing on fibers, on wires, if you like, and so that's the area I've chosen to concentrate on this afternoon. This is really the great discovery, Rick's great discovery of C60, a discovery that really did come in from left field and startled and delighted the scientific community. We've only got to think back to the team of 5 and this very early picture with the 2 proto models down here of C60. That was an immense step forward for science. But it also enabled nanotechnology, because C60 happens to have a diameter of pretty close to 1 nanometer. And you find that it even gets used to try and explain to people just how small a nanometer is. I'm sure all of you have run into various explanations, but this is one I like, that C60 over here is just about a nanometer, and that's about 100 millionth of the diameter of a football, which of course, depending on how it's put together, shares other structural features with C60. But a football is about the same amount smaller than the diameter of the Earth. So a C60 buckyball to a football is the same ratio, roughly, as a football to the Earth. So nano is indeed small, and let's just now focus into carbon nanotubes. It's often said that they were first described by Iijima in Japan in 1991, and indeed 10 years later, Nature brought out a special cover on their edition to celebrate 10 years of carbon nanotubes. But one needs to think a little bit more carefully, because unlike C60, which was a beautiful, pristine discovery, carbon nanotubes have been around probably 2 decades earlier. This is an interesting picture. This was in situ growth in the electron microscope, and it's published in 1974 by Baird & Co. And although the nano word wasn't around, these are nanotubes, and you can see the little iron, or whatever it was, metal catalyst particles tucked in the end. So nanotubes have been around for quite a long time, and it's speculated that people running chemical plants, like polyethylene plants, who had to clear this fibrous carbon deposit out of their plant at regular intervals, were in fact having to scrape out nanotubes. And one way of getting the supply of nanotubes up will be to build a mine on some of these old chemical plants and dig it all up again. I don't think there's any hard evidence behind that, except they're around. Now, this is the key input which Iijima made. Here is C60. At the same time, C70 was discovered, which had got an additional ring of carbons. And then you can go on adding additional rings around the girdle here, C80, and just carry on and on doing that and make a single-wall carbon nanotube. As we've already just seen, they self-assemble very nicely into bundles or ropes. And it's this relationship which really Iijima contributed. So we've got these nanotubes. They are related to C60. And of course, the huge thing is that because of the beautiful science from Rick Smalley and his team to discover C60, the study of soot suddenly became highly respectable overnight. And so it attracted in a different range of scientists. I don't want to repeat what the previous speaker said, but this is just to say that with single-wall nanotubes, there's a whole different range of structures which one can have, the armchair, the zigzag, and all stations in between at different chiralities. And here's the NM, the descriptor of a single-wall nanotube and describing which structure one has, and the fact that they're either metallic or semiconducting, depending on their actual structure. Another class of nanotube are multi-wall nanotubes. They happen to be very much easier to make, And here we've got, like a lot of single-wall nanotubes, nested into each other, rather like Russian dolls. And this is a lucky shot end-on of a multi-wall carbon nanotube. They tend to be, even the internal diameters tend to be considerably larger than the outside diameter of a single-wall tube, and of course the ODs are very much greater. One thing we mustn't lose sight of is that carbon nanotubes are very, very small. Carbon fibers are pretty fine. If you let one go, it sort of gently floats down. But a multi-wall carbon nanotube is about 1,000th the diameter of a carbon fiber. Single wall, perhaps 1/10,000th. Their diameters are much, much more similar to the diameters of polymer molecules. I sometimes say that because I'm really a polymer scientist, to make sure I'm still respectable as a polymer scientist. Because if you look at them as polymer molecules, other things you can do suggest themselves. This is just another picture to the same scale. Polymers we know and love, like Kevlar, and underneath here is a single-wall nanotube drawn to the same scale. They are incredibly rigid, but their size is much closer to the size of a molecule of a polymer than it is to the size of a carbon fiber. How do we make them? Let's just run through three main methods, and it's the Cvd method, which is the most scalable and is by far the most popular, and we've just heard about that with respect to the Rice work. This is, again, a very old diagram from 1978. This is Harrison Baker, telling us basically how a nanotube grows. You have a catalyst or template particle of a metal. Here it's on a substrate. You feed excess carbon into it, having just generated that often by cracking the hydrocarbon gas at high temperature, and it then re-extrudes down here as the nanotube. Basically, that's how they grow. There are a lot of refinements on that. Now, the interesting thing, again, tying in with the previous speaker, is that these metal particles don't have to be on a substrate. They can be free-floating like that, and in fact, one can run them at a whole range of different temperatures. And here we have the free-floating nano-sized particle of a metal which usually chosen so it dissolves a lot of carbon, like iron, cobalt, or nickel, and the nanotube grows out. We were carrying out some experiments. It happened in a vertical furnace, running pretty hot. The feedstock, which we were injecting in, was pretty standard. This sort of mix had been developed again decades ago to make carbon fiber from the vapor route. But there's the basic hydrocarbon, liquid hydrocarbon feedstock, the ferrocene, which decomposes to make the catalyst particles, and a touch of thiophene to put a touch of sulfur in. If you cross-examine chemists, what does the sulfur do? They say, oh, it's well known as a promoter, which doesn't help one very much. And in fact, if one has to go to cast iron metallurgical technology, perhaps from 50 years ago, this is to do with the growth of graphite in liquid iron, where one sees the surface active role which sulfur plays. But nevertheless, we were doing this. And the interesting thing was that as we created this smoke of carbon nanotubes, it did not stick to the furnace wall, but moved down with the gas flow, and then only stuck to the wall where the wall was cold at the end of the furnace. We were running it fairly hot by normal standards, but that's perhaps not critical. This is a video sequence looking up the furnace. Bear with me, it took a bit of time to get the focus right, to actually take pictures looking up a meter-long tube at 1250 is a little bit demanding. But if we can run that, what one will see is a cloud gradually forming in the tube, and that cloud in the furnace tube is coming down towards us. And when we get the focus in, you'll see that it's actually in the form of a sock or a very, very thin tube. There we are. You see the tube curling down towards us and sticking to the furnace wall. Let it run to its full conclusion. We're almost there. So that makes this sort of diaphanous cobweb-type agglomeration of nanotubes stuck to the cold end of the furnace. The next step was to say, is it possible that we can get this cloud of nanotubes out of the furnace without it ever touching the walls? And these are a couple of strategies we thought up. This is a rod which it runs around like that, so it both twists and winds, or we take the cloud and wind it up on a horizontal wind like that. So those were the two ideas, and the intriguing thing is that it actually worked. This is a still where we're looking up the furnace. The clouds here, you can just see the fiber coming down and being wound on this asymmetrically rotating spindle. And on the right, I've got a video clip. I can get it going. Go. There we are. And you can see the fiber coming down and being wound up on the rod. Here we've moved the rod down a bit, so it's looking a bit darker against the furnace. And again, you can see this cloud gradually coming to a fiber. And now we've moved it down even further to enhance the contrast. So it did prove possible to wind it up. The rod on the left has got the fiber made of carbon nanotubes round it, and we've unwound it onto the rod on the right. You can note that the fiber doesn't look all that uniform. At first we thought, oh dear, that's high instability, but in fact it's just that the actual weight per unit length is really very uniform, and it hasn't fully condensed where it looks fatter. We'll be returning to that point in a moment. If we look under the SEM, there's a nice looking fiber. Higher mag, this happens to be a multi-wall one. One can see the preferred orientation. This, of course, has been stretched on winding. And on the right, the image analysis, the width of those peaks is a quantitative measure of the orientation. But intriguingly, you can take the fiber and wind it up, and it holds the twist. It very much behaves more like a yarn, even though it's only, say, 30 microns in diameter. So what have we got? The feedstock can be a very wide range of hydrocarbons. In fact, ethanol works best, so there's a green aspect there. But we get the best fiber properties using a straight hydrocarbon without oxygen, such as hexane, although it's more difficult to spin it. The whole point about the catalyst, the iron ferrocene decomposes to make a very fine nano mist of iron. And we put the ferrocene in just simply by dissolving it in the feedstock, and the sulfur's there to enhance what's going on. The carrier gas we've been using is hydrogen, and those are the temperatures. So what's really going on is that we're making smoke in our furnace, but because the smoke is made of carbon nanotubes, which interact with each other in some way, the smoke is elastic. So we can get hold of this smoke and wind the smoke up continuously, and what we wind it up as is a fiber, or it can be a very thin film. The thing we've discovered is that if we decrease the amount of iron in the feedstock, the yield goes down, as you'd expect, but in fact the percentage of single-wall nanotubes in the yield goes right up. And they're very simple arguments as to why that should be. But there's still a huge number of process variables: temperature, furnace tube diameter, what the carrier gas is, its flow rate, what the feedstock is, the rate of injection, the concentration of iron, concentration of salt, and you go on. And all of this really tells us that we very much are in multi-dimensional parameter space. We've got so many variables, which one do we move next? We try and control it. And this is where we're just changing the carrier gas flow rate and the reaction feed rate. And we found we could spin in this sort of bubble here. This is the average diameter of the nanotubes we're making, with the grey bit being the standard deviation. But the single-wall nanotubes are up in this area, and of course, life's like that. The spinability is, it's more tricky if one wants to make single-wall nanotubes. But this is just an attempt to reduce our variables, in this case just the 2, from the 8 or 9, which we had on the previous slide. This is what the classic high-resolution SEM picture looks like of single-wall nanotubes. We're not looking at individual nanotubes here. We're actually looking at these bundles or swarms, and they appear to divide. That just means that 30 nanotubes are going straight on and 40 have branched off to the right, and so on. It's a very, very typical structure. We can go to high resolution, similar, very similar to some of the slides in the previous talk. And of course, this is where we're getting this beautiful hexagonal packing. The iron, it's possible to clean it out really very easily. And here we have the challenge to, I suppose, a very typical material science challenge. How can we get that order, that structure, all the way across our fiber? If we have more iron, we have bigger iron particles because they run into each other, and we make larger diameter tubes, and here's bright field, dark field of just some multi-wall tubes. So there is an element of being able to dial in the type of nanotubes we want. We're scaling up. Here's a bigger furnace. It's about as big as we can get in a university department, and the furnace is vertical and the wind-up is underneath, and this is the sort of stuff we're getting, just winding it up continuously on the bobbin. This is a video. I hope it's bright enough to see. Before I start it, we're now looking up. You can just see the reflected glow of the furnace here. The fiber's coming down, and this is a spindle. When I ran it earlier, there's some smudging on it. And you can see it's highly amateur. Is that too dark? It probably is. Yes, it is. Anyway, the fiber's coming out here continuously. I think that's not going to work. It's simply not bright enough. Can you see? Yeah. And it's being wound up on the bobbin here. And it just sits there and runs until our injection reservoir's depleted. So about an hour, typically. So it works. We've got a continuous process. A wide range of organic feedstocks work. It goes from feedstock to the product in about 10 centimeters. Some control, yeah, quite good control, whether we have multi or single wall. You don't make a powder, which can have possible health risks. And the electrical and mechanical properties are encouraging, but with very, very good prospects. And we expect that the process could reduce the cost of carbon nanotube fibers to about, my guess is, something like 10 times as much as carbon black, which is a pretty base, cheap commodity product. What's the mechanical potential? Measurements have been made, this is used work, on individual multi-wall nanotubes or very small bundles of single wall. And the amazing thing is the strengths come out to be in the area up to 50 GPa. This is experimental, 20 GPa for single wall with a stiffness of about 1,000 gigapascals, 1 terapascal. That's great news, and that tends to agree with the predictions of the theoreticians, which is also comforting. If we look at the strength stiffness plot for carbon, all the different sorts of carbon fiber, that's what it looks like. Add Kevlar, add steel. But the strength and stiffness of an individual single-wall nanotube is way up there, much stronger than any material known to man by a long way. So there's great potential to be had. But there are, as ever, two challenges. We've got to make very long and perfect carbon nanotubes, and we've got to process them into a fiber so as to realize the potential strength of the building blocks in our final material product. My comment again that because these things are small, the relevance of polymer processing is reasonably apparent. There we are. Those are the sorts of values that are around for individual tubes. And of course, there are those who very much need these properties. This is a very important cover which came out of Rice, out of this group, and with Rick's inspiration, persuading an artist to envisage the space elevator cable, a tethered satellite. And there we are with a magnified view showing how it's got to be made of single nanotubes. There are problems with that associated with micrometeorites and thunderstorms and even the airlines. But nevertheless, it's a vision. Let's just very briefly look at mechanical properties before we go to electrical. This is a plot of fiber strength, and here against this parameter is the concentration of catalyst. And we see that we're getting stronger and stronger fibers if we have less and less, and therefore very much smaller iron particles. And this actually corresponds, the units here, we actually measured them in newtons per tex, which is a more correct way of doing it, and have turned them back into GPa with an assumed density. So things are going up. What does that look like? Well, first of all, the better properties come when we have almost all single-wall nanotubes. How do they compare? Kevlar's up there somewhere, so our best results are of the order of Kevlar for strength. The red ones are the average, showing that there's still a lot of variability in the process, and of course carbon fiber is the next target. If we plot stiffness, in fact we're seeing stiffnesses which we're not really equipped to measure very accurately at the moment, but certainly bigger than 250 GPa, again at the thin end. And of course the energy to break is intriguing. That is also increasing as we go to low iron and increasing a proportion of single-wall nanotubes, and it's even the average is higher than we get from Kevlar and much higher than carbon fiber. So that's an important application area. There's always spider silk and, of course, Ray's results of his coagulation material. Potential for electrical wiring. We've just took our fiber developed for strength and measured its electrical conductivity. It's about 3 × 10⁵. How does that compare? If we have any polymer in with our nanotube fiber, as we'd expect, the conductivity comes way, way down. Slightly better than carbon fibers, considerably better than graphite, but still a long way off copper, as measured, not refined at all. We've done 1 or 2 things. We took a fiber here and we twisted it and looked at the effect of that on conductivity. This is a single-wall fiber, 2 swarms here, or bundles of single-wall nanotubes. And when we twisted and twisted and twisted up to about 2,500 times, as you see the twist, we do lose a bit of the conductivity, which is not really surprising. That's maltreating the fiber. But it's showing just how amazingly resilient this fiber is to other forms of mechanical maltreatment. We do it with a multi-wall. This one isn't fully condensed, and the twisting immediately condenses it. Up goes the conductivity, and then we get the effect as we had before. And we can also get this condensation by dissolving it in acetone dip. As the acetone re-evaporates, it brings the fiber together really very well, about an 80% improvement in conductivity there. And of course, again, as an indication of the maltreatment, we've got this double twisted one. What about for energy applications? Electrical conductivity, we hope to get it up. There's no reason, as we've heard, intrinsically why the conductivity can't be much higher. We're aiming to get the strength up to the very best carbon fibers, if not beyond. The stiffness is pretty good. Energy to break is also quite good. The cost objective is about $2,000 a ton, which is very much cheaper than you pay now, and we're thinking about the mechanical termination for electrical conductivity, the possible electrical applications as it stands at the moment for smart fabrics and wires, and it's quite a lot of wiring where mechanical strength is at the premium, like you have to put a lot more copper in to give the thing enough mechanical strength. For wiring then, electrical conductivity still, as I said, well short of copper. The strength stiffness is approaching carbon fiber. Adding the third one on here, what about power transmission? We've got to do a range of things, very eloquently put in the previous talk, but we've got to obviously make single-wall fibers with good mechanical properties, i.e. we're making a fiber that holds together. We've got to improve the orientation of the single-wall nanotubes, improve the packing perfection, and ultimately, and a key, is to improve the selectivity of metal over semiconducting. And that finishes it. Yep. Acknowledging the sponsors and saying thank you.
Great.
Converting from your measured gravimetric strength to absolute strength, you use a density of around 2.
Yeah.
Seems to be about a factor of 4 too large, and therefore it seems would result in your strengths and stiffnesses being correspondingly too overestimated.
Okay, all our comparisons are properly made in newtons per tex, which is, if you like, the strength divided by the specific gravity. In fact, it's exactly the same number. The density of 2 is the approximation to the ideal packing density of nanotubes if they're aligned parallel and packing. So that's why we use 2. The reason we turn it back into just straight gigapascals is that that is a parameter that people are familiar with, and there are many communities out there away from the fiber community who don't know what newtons per tex means. So that's why it's in GPA. But if we're going to do any serious comparison, we need to do it in newtons per tex.
But the theoretical density, let's say, of a 1010 armchair nanotube, even if it's perfectly packed, is about 1.3. If you look at the micrographs of your yarns, you'll see there's lots of void space. So clearly, the density has to be less than 1. And also, if you look at the multi-wall nanotubes, a large fraction of the volume of the nanotube is a hole that can be fairly large. And since the density of graphite, even the experimental density of graphite crystals is about 2.2, you again must be around 1. Grams per centimeter cubed.
I dispute the 1.3. It also depends on the diameter of the nanotube. As I said, the proper comparison, I believe, should be done in newtons per tex.
I agree.
Not in GPA.
I agree.
And the GPA are put up simply because they are a unit which people can understand and have a feel, and it's a unit you find Kevlar and other fibers expressed in. So in terms of that, I think that's justified. But any rigorous comparison, I think, should be done in newtons per tex, which removes the packing issue.
I agree.
Any question? Not, thank you, Al. Our next speaker will be talking about carbon nanofiber yarns and sheets and alternative materials for energy generation, storage, and transmission. Ray Bauman.
One of the reasons why I was always so excited to come to Rice and to Houston was there was Rick Smalley here, with his enthusiasm, with his ideas, and with his friendliness, and it was his humor. And I and so many people around the world are so saddened that Rick is no longer here. He was such a dynamic person that, and so strong in so many ways that I never conceived of him ever dying. And his unselfish contributions to our work have been just enormous. I mean, without nanotubes that he provided to the world through at no profit through I forgot what it was called, Tubes at Rice. We were able to do our work on the first discovery of artificial muscles, and then our development of the world's toughest material, I believe, based on carbon nanotubes. None of that would have been possible without Rick, and he was always there encouraging everyone. And I just wanted to make these comments to say how much, maybe not only speaking for myself, to be speaking for so many people around the world about how sad we are. Today, I want to talk about a topic that is one that Rick Smalley was very deeply involved in, even up to the point of his death. We all know that individual carbon nanotubes have spectacular properties, thermal conductivities greater than diamond, amazing electrical transport properties, mechanical strengths that are, if you consider the whole cross-section of the nanotube, that are about 35 GPa, about an order of magnitude higher, stronger than in the materials that are presently produced in industry. Provide, exciting possibilities. If only these properties of the individual nanotubes can be realized in continuous wires or continuous sheets. And I'll be talking about our efforts to do this. The work that I'll be describing is collaborative with many people, and one of from a viewpoint of energy is a key focus of a lot of what we do. The idea of making wires for various purposes, from the circuitry all the way up to, for example, cars, wiring of cars. The Denso Corporation is, and researchers working in our laboratory for wiring for cars. And of course, an ideal, a wish for the future, and I think a realistic wish, is to think of carbon nanotubes as an attractive material in the future for the electrical grid in the United States and the world. Again, the types of energy activities we're involved in, as we've discovered, carbon nanotube sheets are effective in converting very small temperature, relatively small temperature gradients to electrical energy. I won't be talking about that, but that's an area in which we're actively involved in the energy area. The nanotube sheets and yarns that you'll be seeing, we've used in a variety of energy harvesting purposes, photocells, both Grätzel and ordinary organic photocells. We use the giant surface area of that carbon nanotubes provide, for example, for artificial muscles. Again, we're converting their electrical energy to mechanical energy. Or in most recent embodiments, we actually use fuels to power actuation of carbon nanotube artificial muscles through a trick. And but again, for these applications, for using carbon nanotubes as fuel cells, we are using the giant surface area of carbon nanotubes, and the fact that in electrochemical environment, these carbon nanotubes, like other high surface area materials, can have giant capacitances, therefore giant abilities to have injected charge at very low potentials, and therefore for actuation, this injected charge causes dimensional change of the carbon nanotube, which is the origin of our actuation. Now, how do you assemble? First of all, before I talk about this, this is an example in which we made carbon nanotube yarns by a solution coagulation process, overcoated it with electrolyte, twisted two together, and then wove these carbon nanotube yarns into a textile using the Martha Stewart method. Now, again, such yarns you could talk about being used for the clothing, anti-ballistic clothing for a soldier. That also provides an energy storage function. These yarns in particular that we used for making the supercapacitor, in fact, are these super tough yarns that are about an order of magnitude tougher than the Kevlar and the Spectra that's used for military vests. Unfortunately, we make the supercapacitor, putting the electrolyte, we have to convert the polyvinyl alcohol using a phosphoric acid treatment to an electrolyte, and that weakens the yarn. But that just gives an example of a supercapacitor application. And again, artificial muscles, carbon nanotube artificial muscles that we make can generate about 100 times the force per unit area of natural muscle, and they can actuate about twice as fast as natural muscle. They're not yet a practical technology because we have problems. The problem really is we have a degree of irreversibility if we cycle many times. Some sort of a electrically amplified creep. It's not ordinary creep because it depends upon the potential in which the artificial muscles are at. We really don't understand this aspect. Regarding the purposes of this conference, here are some of the application areas that might be of interest for the carbon nanotubes, where again, it's very desirable, at least for many of the applications we're considering, to have
more than one functionality. You would like to have, for example, solar cells in which the materials in which you're using for the solar cells have the mechanical properties that you desire. Perhaps support the electrodes could be, for example, supporting materials, provide robustness so a soldier in the desert can unfurl a blanket and use that for harvesting energy. Now, there are basically two generic types of approaches for making carbon nanotube sheets and yarns in the present time. You either can make them by solution or solution processes, and there are a variety of different solution processes, and the solid state processes in which Professor Wendell had just talked about his very exciting work that he's done in Cambridge. Now, I contend that if you want to get the properties for carbon nanotubes of the type that Rick Smalley has been targeting, I think the approach that one is going to have to take is a solid-state processing method. The point is, solution methods are well-suited when you have short nanotubes. However, in order to realize the phenomenal properties of the individual nanotubes and avoid the injurious effects of chain ends, what you want is basically to use very long carbon nanotubes. And the only way that I know to process very long carbon nanotubes is by a solid-state process. So I'll be talking about the rest of the talk about results we've obtained from solid-state processing for forming yarns and transparent sheets that have high strength. And as Professor Wendell mentioned, all of our measurements, as he recommended, all of our measurements of strength are measured normalized to density because of to eliminate any problems in measuring cross sections, often for yarns, which could have 10 microns diameter. This is something I encourage all of those who work in this field. If you're going to report one measurement, report gravimetric strength, because it's easy to measure when something breaks, and it's easy to measure the weight per unit length of a yarn. Everything else can have warts as a consequence of assumptions. Our initial work on solid-state processing of carbon nanotubes build upon pioneering work from China, in which researchers there, they're indicated on this slide, pulled yarns from the sidewall of forest. However, their yarns were so weak to be unusable. We discovered by simply adding a twist, in other words, using the ancient technology of twist-based spinning, we're able to increase mechanical properties by a factor of 1,000 to 10,000. And our collaborator here on this work is Ken Atkinson. He's from CSIRO in Australia. The Australians in this laboratory, he's an expert on wool spinning. So we really are taking an ancient technology and downscaling it to the nanoscale. Here are some yarns that were made in our laboratory by Mei Zhang. Here's a singles, a 2-ply, 4-ply. Mei knitted this yarn, whose diameter is about the diameter of your hair. I no longer mention my hair. But she did this by hand. I'll be talking about strange mechanical properties like resistance to knotting. Now, why do I talk about that? Well, knots are a useful way to, it turns out, for these materials to make electronic interconnects or to make thermal connections. And behavior as a consequence of having knots is important. Also, knots in the sense of, I forgot, they don't call them unknots, but they're called knots, but they're not mechanically knot. Any textile has the equivalent of a knot from a viewpoint of the mechanical effect on the effect of knotting on strength. And so this is an aspect that I'll be talking about later. Our initial yarn spinning process is shown here. Here's a multi-wall nanotube forest. Here's a wedge. We're twisting using this motor at the same time as Mei Zhang with her hand is pulling the motor away from the forest. There we could, our limit of our length of yarns was limited by the length of Mei Zhang's hand. Here's our next apparatus for producing yarn. After we went to this apparatus, we can go to lunch and come back and find 100 meters of yarn. But then we went to our Mark III apparatus. It's a very small jig, which achieves the same thing much more cheaply. Our Mark IV is capable of producing tens of kilometers, but we don't have it working yet. Here's, we are applying our carbon nanotube yarns. Here's 20 filaments plied to make an overall yarn that has the diameter of a human hair. I should mention the benefits are twist unless you have extraordinarily long nanotubes. We have long nanotubes. We have about 300 micron long nanotubes. Unless you have extraordinarily long high nanotubes, the only effect of twisting is to densify. It doesn't include the traditionally accessed effects of twisting in terms of mechanical properties enhancement. Here we've taken those 20-ply yarns in collaboration with 3-Tex. Actually, this braiding was done at 3-Tex and made a braided yarn. So this is a structure that's hierarchical on every scale, on a number of scales. For multi-wall nanotubes, they form bundles. The bundles we make into yarns. The yarns we make into braids. And on the next slide, we'll show you some of the structures we're making right now, are starting to make right now, involving the braids. Here's a fuel cell, yarn fuel cell muscle. I'm sorry, I should have said the wrong thing. We also work on carbon nanotube yarns that are fuel cell muscles. So the slip that I made was natural. Here we talk about just a yarn which is a yarn fuel cell in which we have a braid with the containing catalyst, electrolyte, again, central nanotube assembly, maybe a parallel yarns with a hole in it so that you can get some hydrogen in it. And this is the type of device that we intend to make and weave into textiles, for example. Heat pipes. I won't have time to talk about this, but our carbon nanotube sheets that I'll be talking in the last part of the talk have extraordinarily high thermal diffusivities. The thermal conductivities are, a couple orders of magnitude higher than ordinary plastics, but they're not spectacular. But the thermal diffusivities are really out of sight for these sheets. Now, as far as thermal conductivities, you can just, with a simple heat pipe, you can get thermal conductivities that are orders of magnitude higher than diamond. And the heat pipes are conventionally available. They just involve the transport of a liquid, which could be methanol or it could be an alkali metal that's molten if you want to operate at high temperature, from one end of the heat pipe to the other. And so you evaporate, carrying heat with it, condense, and so forth. Then wick back in the wicking material. We intend to make a heat pipe based on carbon nanotubes that we can sew into a textile that can be incorporated into composite for evening out temperature differences within materials. No matter what material you consider, from spectra or Kevlar used for anti-ballistic vests to a wet noodle or DNA, a strand of DNA, if you knot it and pull it, it breaks at knots. Our carbon nanotube yarns have a very low probability of breaking at knots, and the reason is trivial. The radius of this is a very small radius knot, about 5 microns in a very small diameter yarn. But the radius of this knot is giant compared to the diameter of the individual nanotube. So the individual carbon nanotubes hardly knows it's bent. So there's no degradation of strength. Again, we can tie knots to make electrical connections. We find that there's very little resistance at knots that we tie between two yarns. For the solution, one of the problems with solution-based processing, if it results in simultaneous assembly of carbon nanotubes and polymer, is the polymer gets in the way between nanofibers. And as a consequence, you have very poor thermal electrical conductors. Well, in our twist-based process, we're actually twisting the yarn and then infiltrating polymer if you want to infiltrate a polymer for any purposes. And then the electrical conductivity does not degrade as a consequence of polymer infiltration. The toughness of our twisted yarns is not nearly as high as the toughness we could achieve for coagulation spun fibers, in other words, solution spun fibers that contain polymer that we've reported in Nature several years ago. But the toughness is very respectable enough for the present time that it's usable. For example, our toughness is about 20 joules per gram versus about 33 joules per gram for Kevlar. But remember, if you're not Kevlar, it becomes weaker, loses toughness. You expose it to UV light, it becomes weaker. You heat it up above, certainly above 300 degrees for any extended time period, and it loses its toughness because it chemically degrades. In addition, another aspect that I don't have time to talk about, we can make these yarns so that they deform viscoelastically, but then return to the original deformation. In other words, in that viscoelastic process, we're dissipating about 50% of the energy that's put in during stretch. And so Kevlar or graphite, 5 minutes. Boy, I better stop elaborating. If you normally stretch the yarn containing graphite or Kevlar or spectra, it starts to fail. The elastic energy is released, which tends to further cause failure of composite. Say I'm about 1/3 of the way through my talk. They can be used we use our carbon nanotube yarns for fluorescent lights. They're performed beautifully, or for a very crude type of display that we made. These lamps operate and these displays operate at very low applied voltages because, for example, for this cylindrical fluorescent lamp, what happens is the phosphor is in the outside, the current collector part of the lamp. The yarn is in the center of the lamp. You get two field amplification effects, one due to the fact that from your current collector to your yarn cathode, you're getting field lines converging, but also on each of the carbon nanotube fibers, you got little hairs sticking up, and those hairs further amplify your field. We've discovered also that from before I go on to sheets, and I only have a few minutes to go on to them, 3 minutes and 33 seconds yet, that we don't have to spin from forest. We can spin from other types of economically fabricable arrays of nanotubes. These nanotube arrays should be oriented. Also, the benefit, what twist is really doing is it's doing two things. If you twist a yarn which has very low density, what it's doing is densifying the yarn. That's an effect, part of the effect, but not all the effect. Another important effect is conventional benefits of twisting, in that your twist is providing a force which is laterally confining on the nanotube yarn, causing friction, which holds the carbon nanotube yarns together. But we can also achieve that densification and obtain yarns which aren't quite as strong as those if we maintain twist by using false twist. And what's the benefit of that is false twist is very easy to fast introduce during spinning operation. Also, in our published paper, we've shown for these sheets, we can densify these sheets by just exposing them to a liquid, allow the liquid to evaporate. We can do the same thing in a yarn spinning process. Again, not to achieve quite as strong properties as we can achieve from the twisting. Thing to always remember to take home from this talk. Yarn and sheets that I'm talking about, these processes become easier to practice as the nanotube fibers become longer. There are very specific requirements for forest to be useful in spinning, and it's hard even to tell over the telephone tell someone how to make these forests is difficult. Because it's a matter of turning knobs. But the characteristics, the topological characteristics of these forests that are required, we believe we understand. But I don't have time to talk about that because I have 1 minute and 14 seconds. We've discovered that we can pull from carbon nanotube forests sheets that are as wide as the forest. There seems to be no fundamental limit to the width of forest that we can pull off, width of sheets that we can pull out of forests. These forests are transparent. After condensation using a liquid, their density is only about 3 micrograms per centimeter squared. They have very, very attractive applications possibilities for as transparent electrodes. We've made solar cells from them, and we've made both Grätzel and solid state. We've made light-emitting diodes from them, and they have a number of applications of features that make them very attractive for that application, various type of electron emission sources. And since the time is already flashing at me, I'll just flash through to show you some pictures, if that's all right. Just take me a second. These carbon nanotube sheets, amazingly, have a per unit weight strength. Once they're stronger than sheet steel, but if you pull them in the alignment direction, but that's not a fair comparison. If you apply them and then measure their strength, they're stronger than the strongest sheet steel on a gravimetric basis. They're stronger than Mylar, stronger than Kevlar. So possibilities, for example, solar sail, where Mylar is the material of choice. The carbon nanotube sheets seem to be very attractive. The topology of the spinning process is embodied in some of this picture, but I won't have time to go into that. I'll just flash through some pictures. The nanotube sheets have an unusual self-woven, I call self-woven structure. Perhaps that's almost the best terminology, but the bundles of nanotubes fork and then recombine with forks from other bundles of nanotubes to make a structure which has some lateral extent. From a viewpoint of, again, I talked about the strength. We can make incandescent planar light sources that we can switch in about 1/10,000th of a second because of the extremely small mass of the carbon nanotubes per unit of the sheets per unit area. They provide highly polarized light. We can use the carbon nanotube sheets for microwave welding ordinary plastics together. In this case, it's a microwave heating of the sheets, which causes the plastics to melt weld together. Here, we're targeting heaters for car windows, antennas, and we can make elastomeric. Even though these sheets are strong, we can use a trick to make them elastomeric so they can be deformed over 100% without changing electrical resistance. And we're presently applying that particular feature in very high stroke artificial muscles. And I know my time is overlapped, so I'll thank you very much for your attention.
We have time for one or two questions.
Can I give you 5 more minutes? Is my question.
I think so, yeah. Do we have any more questions? We have any questions? Kenneth?
Thank you for your kind question.
I'm sorry. When you make a solar cell, what kind of efficiencies, or do you ever measure an efficiency?
Yeah, right now, the maximum efficiency we've seen is for an organic solar cell is 2.5%. That compares to 4% for the best organic solar cells right now. And considering the fact that this is an accomplishment in 3 months worth of effort, while other people have been working on these related photocells for decades, I think it's very attractive. But maybe I should really more fundamentally comment on why use carbon nanotubes for photocells. There's a number of answers to this why. First of all, they're very flexible for bending without changing resistance. They have giant surface areas. That means that you can, instead of having a planar interface between an indium tin oxide and a hole transport or electron transport layer, you have the ability of your hole transporting, electron transporting layer to actually infiltrate inside the electrode. So you have giant surface areas, giant possibilities for charge injection. Also, again, this transparency and the tunability of work function is very, very relevant for tandem cells, whether you're talking about solid state or you're talking about Gretzel cells.
Ray, you said that it was difficult to make your forests, but to make forests in general is really rather easy.
Yeah.
So I'm wondering what's special about your forests.
The Mei Zhang is what's special about our forest. I have this remarkable researcher.
But is she scalable?
Once the apparatus is set, the dials are set, you can keep on making the forest. The forests grow very fast. So in a commercial process, if we use the forest approach, we would be growing nanotubes on one end of a belt or one end of side of a drum and scraping them off, pulling them off as fibers or sheet on the other side. The key thing is you need to have intermittent bundling within your nanotube forest. That means you have to have lateral connectivity. If the new nanotubes are not connected with other nanotubes in the forest, you pull and you pull off just a nanotube. If they're too connected, you pull off a chip of the forest, and that doesn't do you any good. The forests that we're using, let's say, have 300 micron heights, and they have a diameter of about 10 nanometers, so an aspect ratio of about 30,000. That means if you look at this forest as a bamboo forest, you have an inch diameter nanotubes that go half a mile high. Now, as they go from the bottom of the forest to the top, they bundle. They form small bundles to the left, to the right, to the left, to the right, and that provides a degree of connectivity. We look at etch pits in the bottom of the forest, left where the nanotubes are growing out from. It's not appropriate to call them etch pits, but you can see a morphological changes where the nanotubes were. And you count those, and we can get a range, low-density range where just nanotube spinning will not work, and higher range where it will. Well, you could use a braid on the inside, but a hollow braid, for example. Yeah. Or it's porous. I mean, these braids, the density of our twisted yarns is about 0.8 gram per centimeter cubed. There's no iron. There's very little iron in them, maybe 2% maximum amount of iron. So, you have porosity.
So you think it's enough to have enough hydrogen inside?
Well, you can either braid your inside so that you have a hole, or you could use the porosity, but and they're limited as far as rates at which you can diffuse things in. Uh-huh.
We heard from Alan that as he got lower iron, he got stronger yarns. I assume that's because he was getting more single-wall nanotubes. Would you suggest that all of your properties would be dependent on whether they're multi-wall or single-wall, and will they get better if you move more toward a single-wall forest?
I think fundamentally, if you're talking about bundled multi-walls, single walls, or bundled multi-walls, I think it's fundamentally the same issue pertains. If you have short nanotubes, then if you're gripping basically on the outer, the outside of the bundle or the outside of the multi-walled nanotube, there's a problem of stress transfer in the inside. However, this problem goes away in terms of electronic transfer from outer tubes to inner tubes and for mechanical transfer if your nanotubes get long enough. And again, we're doing this spinning process right now for multi-wall nanotubes that are 300 microns high. The same process could be practiced for single-wall nanotubes just as well as for multi-wall nanotubes. And people already, Ejima and Hata in Japan, can grow 3 millimeter long high forests. So the pathway to getting improved properties of all types seems to be evident.
Call a halt to the 5-minute question period. And thank you again, Ray.
Thank you.